Hello everyone. In the previous video we have discussed about what is search and how state space representation helps us in solving various problems using search algorithms. We have also seen terminologies like frontiers, reached, open list, closed list, and let us see now one of the uninformed search algorithm called as breadth first search, and what is the pseudocode for it, how do you implement it, and what is the time complexity, space complexity, whether is it complete or optimal. So let's see all those details. So first, breadth first search, as the name implies, it traverses along the breadth before it goes to the next level. So first it completes all the nodes and then it goes to the next level of nodes of next level. So this figure clearly shows here that A, B, C, D, E, F, G. So first A and then completes B and C, which are in the second level, and then goes to all the D, E, F, G, H in the third level. So it follows, the implementation follows a data structure called as a queue, which is first in first out, and new nodes always go back of the queue, and we always pop the top node and we try to expand it. So at each state we are supposed to see whether the goal node, we have reached goal node or not. So on this particular aspect the algorithm differs, especially the next algorithm called as uniform cost search differs in the implementation exactly at this point. So once a child node has been generated, in breadth first search we immediately test whether if it is a goal node or not. Whereas in other algorithms like uniform cost search we should not do it. The reasons will be explained there. So here, so we are supposed to test whether the node, the child node which we have got is a goal node or not. Once it is a goal node, we stop searching the algorithm, because the breadth first search also guarantees the optimality. So it is a complete algorithm, and it is also, it generates an optimal path. So once you reach to the goal node, there is no need of searching for another path, because it is already guaranteed that it is optimal and it is complete. It is optimal in the sense that there will not be any other path which can generate a better solution than this. And if you see the time and space complexity, apart from completeness and optimality, we also look for time and space complexity in breadth first search. Both time and space complexity are worse in BFS, breadth first search. So if you see more details of how much time complexity it has, consider a node which generates B successors, and once again each of these successors generate B successors, which means that if at all, if you have a depth of D layers, and at each layer each node is generating B successors, you will have a total number of nodes as B plus B square plus B cube and so on, B power D, which is if you represent in big O notation, it would be big O of B power D. So the worst case complexity would be B power D, which is way above. So in order for you to test whether it is a goal node or not, you need to visit each of those nodes, and the number of nodes are in the order of B power D. So the time complexity is order of B power D. And the important thing to note is the space complexity is also very high, because we store literally every node in the reached state, and we verify whether a particular node has been reached, whether is it already been generated in the frontier or reached, which means that you need to store all those nodes somewhere. So the space complexity is also huge in breadth first search, and so both explode set and frontier set will have the order of b power d. Okay, so the memory requirements in breadth first search is very high. Now let us see a pseudocode for breadth first search. So we will also be seeing step by step how these frontiers and reached, open list and closed list are used, and how the goal test happens. So this is a tree. On the right side we have around 3 plus 5, 8 nodes, and G is the goal node, or you can say goal state. So we would like to start from A and we would like to reach to G. So the pseudo code of breadth first search goes something like this. So first we initialize with the starting node, which is A, and we immediately test whether is it a goal node or not. If it is a goal node, we stop there because we don't pursue any other, because it is optimal and it is complete. And but here in this case A is not the goal node, so we move forward and we first store this node in frontier, and you can see in the bottom the frontier contains A and the current node is also A. Explode set is currently empty because we haven't generated any children successors of A, so currently it is empty. So we start a loop where first we check if the frontier is empty. If the frontier is empty, there is no the search is completed, but the frontier is not empty, we have the node A, so it fails, so the if condition fails. So if we go to the next state and we pop from the frontier. As we know, in breadth first search we follow first in first out queue, so whichever comes first we will be popping the ones first. So here we only have one node, which is A, so we will be popping that and we keep it in node A. And once we pop it, we also keep this node into the explode set A. So now we generate the children of A, we find out the successors of A, and then we try to store it in the frontiers, and also first we see whether are they goal nodes or not. So we generate the child node. So here the child node is B and C, so let's start with B, and if this child node is already existing in the frontier or reached nodes, it is not available as of now. So the node B is not there in frontier and explode nodes, so it is satisfied. So we go inside and test if this is the goal node or not. Is B a goal node or not? Here it is not a goal node, so the condition fails. So then we keep this node into frontier and for later expansion. So the frontier contains all the nodes which have been reached but which are supposed to be expanded, or which are supposed to be the children of that particular node are still yet to be generated. So frontier is an boundary between the nodes which have been already generated and expanded and the nodes which have not been reached. So here once we encounter a child node, we test whether it is a goal node or not. If it is not a goal node, we keep it in the frontier. And so the next state we go, so we have completed one child node, so the next child node is C, so we take that as a next child node and we see if it is already present in explode or frontiers. If it is not there, we try to test if it is a goal node or not. If it is not a goal node, once again we keep it back into the frontier. And once we have completed for both the children, which means that we have completed one cycle, so then as per the breadth first search, we take the first node from the frontier. So we follow first in first out. So B is the first node which is lying there, so we pop the node B and we try to use that node B for further expansion. So node B has children D and E, so we place node B into the explode node because we are about to generate the children of B, node B. So the first child of B is D, so this child D is also checked whether it is already present in frontier or the explode nodes. D is not present, so we try to test if it is a goal node or not. If it is a goal node, we stop it there itself, but it is not a goal node, so we place that in frontier. So as you can see, every time when we place a frontier, we are keeping towards the end, which means that we are following the first in first out. Only after we complete pursuing the nodes which reached early, we reach to that particular node. So now the frontier contains D. So we also have another child which is E, so we pursue that and we also place the child node E in the frontier. So once we have seen we have not reached to the goal node, so we go to the other node in the frontier for further expansion. So we will pursue now the node C. So we have popped the node C and considered for expansion. So and we also place that in the explode nodes now. So the nodes which are in red color means that they have already the childs are about to generate or it has been completed. So here for C we are about to generate. So now the first child node of C is F. So this F node, we see if it is already present in frontier or explode. It is not there. So once again we see if it is a goal node or not. If it is not a goal node, it goes to frontier. And in the same way we do it for another child which is G. So now the child node G is, we see if it is already present in frontier or not. If it is not present, it goes inside and C tests for whether it is a goal node or not. If it is, here it is a goal node, so now here we satisfy it and we stop it here. So because we reached the goal node G. So the important thing to remember here and is we are immediately testing for the goal node once the child node has been generated. This is very important because in the uniform search cost, uniform cost next algorithm, we have, this is one of the important difference we make sure, so because we should not test for the goal node immediately after generating the child in the uniform cost search, whereas in the breadth first search we try to do it early. So that we will see in the next algorithm. So now let's summarize the time complexity in comparison with other algorithms. We are going to do comparison for every algorithm. Here we have seen the breadth first search. Yes, it is a complete algorithm and it is also optimal. So so the breadth first search, usually the path costs are all uniform or equal. So we are assuming that the paths are all having equal costs. So in such cases it is optimal and it is also complete, and the time complexity and space complexity is worse. We have seen order of B power D, where B is the number of branching factor and D is the depth, number of levels in a tree. So in this way we develop breadth first search, which is an uninformed search algorithm which does not take into consideration where an estimate of the goal state, any knowledge of it, and attempts to reach to the goal state. So we have reached from the initial state to the goal state, and it has a tremendous amount of time and space complexity, but it assures that it will definitely reach to the node in an optimal way. So this is about breadth first search algorithm. We will be seeing the other uninformed search algorithms in the next video.